Hello everyone, welcome back to logicbinder. In today's video, we shall learn few more examples of construction of DFA. First example is construct the DFA accepting any string except AAB defined over the input A, B. Let us assume a language L of M is accepting AAB. Then the language L complement of M is rejecting AAB such that the relation is given as L complement of M is equal to L of M minus AAB. It means L complement of M is rejecting the string AAB from the language which is accepting the string AAB. So that initially we have to construct the DFA for the language which is accepting AAB. Then after we have to design a DFA which is rejecting the string AAB. Initially, construction of a DFA for the language which is accepting the string AAB, nothing but L of M. The minimal automata is given by processing the basic string which is nothing but AAB. So from the initial state Q0 we are processing the string AAB through the final state Q3. For this minimal automata, upon giving a remaining input transitions, we can get the complete DFA. So DFA is given as Q0 on A is already completed. Q0 on B can be given to the same state because the DFA should accept the string AAB. Q0 on B cannot be given to Q1, Q0 on B cannot be given to Q2, Q0 on B cannot be given to Q3. So the only possibility here is Q0 on B should be connected to the same state Q0. Similarly, Q1 on A is already completed in minimal automata. Remaining is Q1 on B. It should be connected back to the Q0 state in order to get the string in the form of AAB. And Q2 on B is completed here. Remaining is Q2 on A. So here Q2 on A, if it is connected to the Q2 state, the string observed is BAAAB. So which is a valid string. This connection is valid. And Q3 upon both A and B can be connected to the same state, so that the sample strings observed are BAA, AB, AAB, BB, AA, ABA, so on. Here for the language L of M, we have designed the DFA. For the complemented language which is nothing but L complement M, that is a language which doesn't accept the string AAB or which reject the string AAB, we have to convert the final state to non-final state and non-final state to the final state for the above plotted DFA. So in order to construct the DFA for the language which is not accepting AAB or rejecting the string AAB, nothing but L complement of M, we have to convert the final to non-final state and non-final to final state. So consider the DFA of the language L of M which is accepting the string AAB. Here if we observe Q0, Q1, Q2 are non-final and Q3 is a final state. These states will be converted here. Upon converting the final state to the non-final and non-final to the final state, we get Q0, Q1, Q2 as a final states and Q3 as a non-final states. The transitions will be remaining same here. And let us observe what are the sample strings which are processed through the final states. Here Q0, Q1, Q2 are final states. So the strings which are processed through each final state will be observed here. Consider this DFA for a language which is processing the string other than AAB. Here the sample strings are BBB. If Q0 has a final state, since it is a loop on B, so the string will be B, 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 so on. And the string BA, BA, if Q1 is final state. Here BA, BA is processed through Q1 as a final state. If Q2 is a final state, the sample string processed can be B, B, A, B, A, A with Q2 as a final state. Thus, above DFA can process or accept the string AAB through any final state, either Q0 or Q1 or Q2 as a final state. One more example is construction of a DFA for a language starting and ending with same symbol over A and B. Here we need to construct a DFA for a language which is starting and ending with the same symbol. Let us assume a language is L of M with the strings W which are in the form of A, W, A, B, W, B for all the strings belong to sigma star. Since the language is containing the same symbol either at the beginning or ending, we can include the empty string. So epsilon, AA, BB, ABA, BA, BB, AB. Here all the strings are starting and ending with the same symbol. Thus, the minimal automata for this language is given by, from the initial state Q0, on reading the first symbol as A, it is reaching the state Q1. Since the ending symbol should be the same symbol, so Q1 on A is moving to the same state with Q1 as a final state. And again from the initial state Q0 with B as a first symbol or a starting symbol, it is reaching the state Q2. Since the ending symbol should be the same symbol, so Q2 on B is moving to the same state Q2, making Q2 as a final state, so that the starting is A, ending is A, starting is B, ending is B. Upon giving a remaining input transitions to this minimal automata, we get the complete DFA. In the minimal automata, Q0 on A is completed, Q0 on B is completed, Q1 on A is completed, Q2 on B is completed. Remaining transition we have to give. So Q1 on B should be connected to any other non-final state which is Q3, and Q2 on A should be connected to the any other non-final state which is Q4. For this Q3, Q4 also we have to mention A and B transitions since it is a DFA. So Q3 upon reading A should be connected to the final state because the language is starting and ending with the same symbol. So to the final state the last input symbol should be the same as a first input symbol. So Q3 upon reading A should be connected to the final state since the first symbol is A here, whereas Q3 on B can be connected to the same state so that the string will be A, B, 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 A. Starting and ending symbol is same here. Similarly, for this particular B path, Q4 upon reading A can be connected to the same state, whereas Q4 on B should be connected to the final state Q2, so that the string will be B, 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 A, B. Starting and ending symbol is same in this particular path. Construction of a DFA for a language starting with 1 and ending with 0. Let L of M is a language. The sample strings are 10, 100, 100, 100, so on. Here all the strings are starting with 1 and ending with 0. Thus the minimal automata will contain the starting symbol and ending symbol. So Q0 on 1 moves to Q1, on 0 moves to Q2. Upon giving the remaining input transitions, we get a complete DFA. So in the DFA, we observe that Q0 on 1 is already completed. So remaining input is Q0 on 0. Since the first input is 1, the input should not be 0. So it is connected to the trap state which is Q3. Q1 on 0 is already completed in minimal automata. So Q1 on 1 can be connected to itself. Similarly, Q2 should be defined with the 0 and 1 transitions. So Q2 on 0 can be connected to the same state because the last symbol should be 0. And Q2 on 1 should be connected back to Q1 state, or it can be connected back to the Q0 state. So here we have connected to the Q1 state. Similarly, since it is a DFA, we have to mention both 0 and 1 transitions to the trap state also, which is a Q3. So Q3, which is a trap state, upon reading either 0 or 1 will be in a same trap state which is Q3. So the sample strings are 10, 110, 10, so on. So this is a valid DFA which is processing the string starting with 1 and ending with 0. Construction of a DFA which accepts either 00 or 11 as a substring. Let L of M is a language. So the sample strings are 00, 11, 0100, 10110, so on. Here in all the strings, the substrings are either 00 or 11. So in the minimal automata, we have to process 00 in one path from the initial state and 11 in one path from the initial state. If substring is 00, the path is Q0 on 0 moves to Q1, Q1 on 0 moves to Q2, which is a final state. If the substring is 11, the path is Q0 on 1 moves to Q3, Q3 on 1 moves to Q4, which is a final state. Here in this path, we can generate a substrings as 00. In this path we can generate the substrings as 1 1. Here Q0 is the initial state and Q2 Q4 are the final states. For this minimal automata, upon giving a remaining input transition we get a DFA. In the minimal automata, Q0 on 0 is completed, Q0 on 1 is completed, and Q1 on 0 is completed. Q1 on 1 should be connected back to the Q0 state, because here we are having two consecutive zeros or 0 0 as a substring. Q1 on 1 cannot be given here to Q1, or Q1 on 1 cannot be given to Q2 state. So Q1 on 1 should be connected only to the Q0 state. Whereas it is a DFA, Q2 on 0 1 can be connected to the same state, so that the sample string will be 0 1 0 0 0 or 0 1 0 0 1. So Q2 on 0 1 can be connected to the same state, because after 0 0 we can have any number of zeros or ones. In this path, Q0 on 1 is completed, Q3 on 1 is completed. Here Q3 on 0 can be connected back to the Q0 state, because here 1 1 is a substring. Q3 on 0 cannot be connected to Q3, Q3 on 0 cannot be connected to Q4. So Q3 on 0 should be connected only to the Q0 state. Similarly, Q4 on 0 1 should be determined here. So Q4 on 0 1 can be connected to the same state, so that the string will be 1 1 0 1 1 1 1 0 1 1 0, so on. The sample strings are 0 0 0 1 0 0 0 1 0 0 1 0 1 0 0 1 in this path, with 0 0 as a substring. Here the sample strings with 1 1 as a substring are 1 1 1 0 1 1 1 0 1 1 0 1 0 1 1 0, so on.